Chapter 8 begins a new segment in the book on nonparametric statistics, or what I like to call non-P. Chapter 8, 9, 10, 11, and 12, so a lot of the rest of the book is on nonparametric statistics, but we're going to start easy today with the Bootstrap. Before we do that, though, I want to talk a little bit about what nonparametric really means. So non-P means no model. You might think they would call it model-free statistics instead of nonparametric, but the reason why will be apparent in just a moment. So that means no YI, IID Gaussian, or no YI, IID Bernoulli. So none of those things, no Poisson distribution, no gamma, no exponential, none of the other things that you might come across in your homework and so on. Now these models have parameters. So all of the standard distributions have parameters. So if you're not using one of those distributions to describe your model, then you're also not using or estimating those parameters. So none of that, but that doesn't mean you don't have other things that are usually involved with statistics and probabilities. So still have concepts like IID and mean or expected value of observations or variance, right, var. So we still have many probabilistic or statistical concepts, just no model and no parameters that go along with that model. So that means fewer choices or assumptions that might be questionable in any analysis. And so by having fewer of those assumptions, you have a more robust analysis. At least that's how the thinking goes. We've kind of seen some of that before. Remember the central limit theorem. The central limit theorem involves fewer assumptions. You don't need to choose a model, although we always used it in a modeling context. So the CLT can be non-P, but in chapter 4, in all of the examples in chapter 4 anyways, we used it in a parametric context. So P and non-P. All right, you'll get to see a lot more about what I mean over the next several chapters, beginning right now in part A of this video vignette with the Bootstrap. The Bootstrap is perhaps the simplest and also one of the newest, so the most modern non-parametric method in statistics. It's ideally suited to working with a computer, to simulation. So that's the reason it's modern. There are other procedures that are non-parametric that are older, that are better suited to particular situations, and we're going to see a lot of those over the next several chapters. But the Bootstrap is really simple and really powerful in the sense that it's broad. You can apply it in a lot of different settings. But I think maybe the most important thing is that it's inherently simulation-based. And the main idea, the main procedure that gets used is sampling with replacement. It's such a simple idea. In R, we use the sample function in order to perform a Bootstrap. And I'll show you what I mean by that. So let me describe a bootstrap for you. So consider any statistic of interest. Now remember, a statistic is just some function of your data. You don't have to have a model to think about a statistic. However, if you do have a model, often a statistic naturally suggests itself. So our statistic is just some function of the data values. For example, you could sum them up and divide by how many there are. So you could calculate y bar, or you could take the middle one. That would be the median of these y values. Or you could do the estimate of the standard deviation or its square. All of those are just functions of the data values, so they are statistics. So think about one of those statistics. What I present here is going to be focused on the median because it's novel to us. We haven't talked about it before, but I'm also going to show you some stuff with S, with the estimated standard deviation. And it's really easy to substitute in for the mean, y bar, the average, if you want to do that instead. So I'm going to draw a diagram here. I'm going to represent the data as a column of values. So those are the data values. And with that column of values, I could calculate the statistic that I'm interested in, like maybe the median. Okay? Or I could randomly resample. So let me draw some arrows here. Dot, dot, dot. Okay, not the best artist. Actually, I could probably do better than that, right? Let's see. There's a better arrow. So each one of these is a sample with replacement from the original y values, y1 up to yn. So each one of them would give me a vector of y1 stars, or y2 stars, or yb stars. So b will be the number of Bootstrap resamples. So each one of these y star vectors is a resampling of the original n data values. When you resample with replacement, you end up with some copies, a random number of copies of each one, and you may be missing some of them. In fact, if you have any copies or duplicates, you will be missing some other ones. And for each one of these Bootstrap samples, I can calculate a statistic on that sample. Careful here, when I write S up here, I'm thinking about these are standard deviations. Maybe that would be better to write. So standard deviations or variances. Whereas when I write the S statistic, I'm thinking about generically some function of the data. It's unfortunate that statistic and standard deviation start with the same letter. All right, and then the last one, like that. So I'm going to calculate the statistic on these random resampling with replacement of the original data values. And then this collection, that's again an ugly, man, it's hard to draw on your side. So there we go. That's what I'm looking for. So this is a collection of sampled statistic values. So it forms an empirical distribution. An empirical sampling distribution. That would be called the Bootstrap sampling distribution. So let me show you what I mean by going over to R. Here's some data. These are lengths of fish in inches caught during a tournament a fishing tournament in the Chesapeake Bay. Okay, so how many observations do I have? I have 31 of them. And suppose I'm interested in the median. Okay, so the median is, whoops, not capital Y, lowercase y. So the median is the middle value in the data. If it's odd, if it's even, it's the average between the two middle values. But this data set has a length of 31, which is odd. So it's the middle data value in the data, and that's 18.1. So suppose I wanted to understand the sampling distribution of the median without making probabilistic modeling or assumptions. Okay, without choosing a distribution like a Gaussian or something else like that. I could sample with replacement. So for example, I could create a y star, which is a sample of the original data values y. I'm going to get a sample of the same size n as the original data set, and I want to sample with replacement. Okay, so this y star is a data set that I get from my original y's randomly resampled with replacement. And each time I do this, I get a different one, right? So there's a different y star. You can see they have a different first value and a different second value, but they all come from and are the original data set y. It's just that they have some duplicated and some missing. For example, if I do table y star, I can see that it has 2 copies of 7.1 and 2 of 10.5 and 3 of 21.7 and 3 of 32.8 and 2 of some other ones, but 1 of the rest. And I'm also missing some. If I do set difference between y and y star, I can see, oops, set diff. I can see that these 1, 2, 3, 4, 5, 6, 7, 8 values were in my original data set y, but they were not in the randomly resampled one y star. So I'm drawing from the data and getting a new data set, kind of like a virtual data set that's coming from the original data as if the original data were itself the distribution. So thinking about some of the simulations we did before, we would get a y star by sampling from a Gaussian or sampling from a Bernoulli or whatever. Here we're getting the random data set by sampling directly from the data itself with replacement. So I'm not making any distributional assumptions except that the y's themselves are the y's that I've got. So they're kind of taking the place of the distribution, which is interesting and magical, I think. So we're not going to do this just once, right? We're going to do it a lot of times. So a Bootstrap resample is lots of those. Okay, so I'm going to do a lot of them. I'm going to call the number of them capital B to remind myself that I'm doing a Bootstrap, but this plays the same role as capital N does in our simulations from earlier in the book. For B in 1 to B, y star is sample y and replace equals true. And then I better save all those. So I need to make a big matrix to be able to store all of these samples. Oops. I didn't. I'm being sloppy. Okay, there we go. So now I've got a big matrix storing all of these resamples. Now, what to do with that? Okay, so there's a bunch of things you could do with that. I'm going to focus on the median. So I could calculate my statistic of interest. So just following along in our diagram, right? I just did the sampling part, and now I'm going to do the calculating of the statistics part. Okay? So I'm going to do apply, which lets me give a matrix, and I'll apply over the rows of that matrix the statistic median that I'm interested in. So these are my Y meds. Okay. Another way to do this would be to do Y meds B and then calculate the median directly. And in fact, if you do that, you don't need to save all these intermediate samples. But I'm choosing not to do that because I'd like to just have a generic set of Bootstrap resampled values so that later I can apply any function I want to them to get my statistic. And then I can look at the empirical distribution with, I like histogram, just like with our other simulations. Okay, so I don't think you can see that until I reveal it. So there you go. There is my histogram of medians that I get when I resample the data. They apparently include a lot of this number here, which is like 18. And then there's a bit of a gap because I think that's because there's no data values in the data that are between 16 and 18. So that never comes up, and then 16 comes up a bunch. It's interesting to look at this in the context of the range of the original data. So you can see that the original data go from much less than, or a little bit less than 10 to much bigger than 30. There are some values that go way out to 50. So it may look like we haven't distilled anything, but these medians cluster a lot closer to the left part of the data than the very biggest ones in the data that go somewhere as big as 50. There's some very big fish in this data set. Okay, so going back to the whiteboard, I want to write something down that I think is really important. The Bootstrap resamples, right, that's these guys here, are best understood or utilized in a confidence interval calculation. Okay, so that's what I'm going to talk about first. Now I want to use these samples in a confidence interval calculation for the median, because that's what I've got right now. So I'm going to choose some probabilities for my confidence interval, and then I'm going to use the quantile function with my medians with those probabilities, and then that'll be my confidence interval. Okay, so my confidence interval for the median statistic goes from 11.9 to 2.17. And if I want, I can put that on the graph. V equals Ci, col equals 2, right? So those values, 11.9 and 21.7, span 95% of the sampling distribution of the median. So that would be my confidence interval. Now, you've noticed probably that this sampling distribution is discrete and very sort of choppy. Another popular thing to do for confidence interval calculations with a Bootstrap especially in this situation where the discrete nature of the distribution could potentially be concerning, is to use the central limit theorem, or really what you're using is just a Gaussian approximation. But there is a sense in which you're doing a central limit theorem too, but I don't really want to get into that instead. So what that means is take the average of your medians and then add in the Q norm, so the quantiles you get from a normal distribution for those probabilities, and multiply by the standard deviation of those values. So instead of using the quantile function, which only takes values that are in those medians, and those values are only, there's only 1, 2, 3, 4, 5, like maybe 10 unique values out of the 31. Instead, you're going to use a formula that assumes that the medians are on average Gaussian, which they would be on average, to make the calculation. But you don't get a very different interval in that case. So if I put this on there, it's called a CI G for Gaussian, and then I do AB line with that and make it dashed. You can see that the left one is nearly identical and the right one spread out just a little bit. So that's an alternative way to make this confidence interval calculation. Okay, so oh, you can't see that. My apologies. I do that way too often. So there's the plot of that with a dashed line there, very close, and a dashed line there, very close. So two different ways to use the Bootstrap resamples to calculate a confidence interval for, in this case, the median, but you could do this with any statistic that you want to. In fact, why don't we try, let's do the same thing for S equals the standard deviation of Y. So let's just calculate S. So that's S is SD of Y. So that's on the data values, right? And then I can go grab this apply function. I've already got the Bootstrap sample, so I don't need to do that again, and do the SD instead. And then I can show you that. This is less choppy because it's not selecting just one data value from the original data set for each median calculation. Each SD on each different data set is a different residual sum of squares, or square root of a residual sum of squares. So it's not going to have the same kind of choppiness. And then I can calculate confidence intervals. So I can do CI is quantile Y star, not Y star, YSDS P. So my confidence interval for the standard deviation is 7.8 to 15.2. And I can put that on the plot. There it is. And if you want, I can put the original statistic S on and Y equals 0. Right, so that's the original estimate. I didn't do that for the median example. Probably should have, but I didn't think of it. This is what we calculated, but on its own we don't have any uncertainty. But with the Bootstrap, I get the whole distribution of those values without making any distributional assumptions for the original data, and I also get a confidence interval. And if I want, I can calculate a Gaussian approximation with mean of YSDS plus Q times SD of YSDS. Oops, it's not called Q. What did I call it? Oh, I did Q norm of P. And then AB line V equals CIG, not CIQ. Oh, I got a sad face in there. Whew. Must be getting late in the day. There we go. Whew. So you can see there's not much difference there between those two different confidence interval calculations. All right, the last thing that I want to tell you about involves testing hypotheses. The simplest way to test a hypothesis with a bootstrap is to invert the confidence interval. So what do I mean? If the value you're wondering about, so right, that's your specified by your null hypothesis, is outside the confidence interval, then you can reject the null hypothesis at whatever level the confidence interval is. So the confidence interval is a 95% interval. That's an alpha of 5%, and so you would reject at the 5% level. So looking back at this plot here, or at these confidence interval calculations, if I wanted to test a hypothesis about sigma, and I wanted to know, could sigma be 10? Well, 10 is in that interval, so I wouldn't be able to reject that null hypothesis. But if I was testing about 6, I would be able to reject that hypothesis. So that's the bootstrap.